So we are continuing our discussion on the power spectral density of stationary processes. So we observed that the spectral characteristic of signal which are associated with the random process defines the spectral characteristic of random process. So if the signal of the random processes are slow varying, then random process will mainly contain the lower frequency component. And whereas if the signal changes rapidly, then the random process will contain high frequency component. So that is the basic correlation with the variation of signal or the changes within the signal with the random process. Now we further analyze the power spectral density. That is another statistical term which is very important for the analysis. So power spectral density symbolically represented as Sx of f. So if you observe, it is nothing but the time to frequency domain correlation, that is power spectral density of random process xt can be given as Sx of f. So Wiener-Khinchin theorem tells us the power spectral density is nothing but Fourier transform of autocorrelation function. So we can say that power spectral density and autocorrelation functions are related with the Fourier transform with each other. Now this is valid for stationary process only. So remember, whatever definitions we are observing, we are simply dealing with the stationary process. So this power, if the power spectral density is related with Sxf, then what is the power? Power is nothing but integration of density function. So power spectral density had been integrated from minus infinity to infinity with respect to f. That will gives you the total power. So that is the power calculation method corresponding to with the help of integrating power spectral density. Now we are also aware that from this relation, this Wiener-Khinchin theorem tells us Sxf is nothing but the Fourier transform of autocorrelation function. So we can put it like this one, that is autocorrelation function is nothing but the inverse Fourier transform of power spectral density. So we can write it as Rx tau is equal to minus infinity to infinity Sx of f e to the power j 2 pi f tau df. Now putting tau is equal to 0. So if you put tau is equal to 0, you will get Rx 0, that is equal to e to the power 0 will be 1. So integrating Sx f df from minus infinity to infinity. So you will result in this function Rx is 0 is equal to minus infinity to infinity Sxf df. Now if we compare this relation with the relation of the power, so we will simply observe that by comparing these two relations, we will observe that power is nothing but the autocorrelation function value at 0. So if you are having autocorrelation function with you, put time value is equal to 0, that will give you the total power of the signal in itself, right? So that is the power spectral density and its correlation with the autocorrelation function and the power. Now power spectral density in the LTI system. So we had observed random processes with the LTI system in time domain. In fact, we had done these expression analysis in the previous slides. That is my, mean of output, is nothing but the mean of input integration of minus integration of impulse response of the system right from minus infinity to infinity. Similarly, autocorrelation function of output is nothing but autocorrelation function of input convolve with impulse response and again convolve with h of minus tau, that is the indexes had been negative, inverted index. And then cross correlation function is nothing but cross correlation between input and output is nothing but autocorrelation function convolve with h of minus tau. Now these three relations are defined in time domain. Now I want to convert it into the frequency domain. So if you convert it into the frequency domain, you can simply correlate with what is the minus infinity to infinity ht dt. In frequency domain, it is nothing but if ht is the having Fourier transform of capital H of f, then minus infinity to infinity ht dt will gives you capital H of 0. So in the frequency domain, this my is equal to mx into h of 0. Similarly, this autocorrelation function of output is nothing but, in the frequency domain, it is related in terms of power spectral density of output is equal to power spectral density of input multiplied by HF, that is the mod of HF square, and it shows that the power is independent of phase of the system. So it is simply mod of HF square. And similarly, cross correlation function, so that is nothing but power spectral density term of the cross correlation function is equal to SXF into HF. So this shows the frequency domain representation of these three signals, and I will suggest you to find out or to draw these signals with the help of these signals and the Fourier transform. It will be better, create a better understanding about the analysis perspective. Now, another important process is the power spectral density of the sum processes. Now, what are the sum processes? Sum process means you are having addition of two signals, and in most of the, or in many practical cases, we observe that any outcome is represented by additive nature, and as far as our syllabus is concerned, we will observe that we are dealing with the addition of the signals. So we will simply try to converge up to certain relations, and we will further use them in our subsequent analysis. So let us assume that ZT is a random process which can be represented by xt plus yt, where xt and yt are jointly stationary random process. So ZT is also a stationary process with the function as rz tau is equal to rx tau plus ry tau plus rxy tau plus ryx tau. That is, autocorrelation function of ZT is equal to autocorrelation function of x plus autocorrelation function of y plus cross correlation function xy plus cross correlation function yx. Now, taking the Fourier transform and performing certain manipulation, we will observe that the power spectral density corresponding to Z is nothing but power spectral density corresponding to x plus power spectral density corresponding to y plus 2 times real part of SXYF. Now, if the two processes xt and yt are uncorrelated, then simply we can write the cross correlation function of rxy tau is nothing but mx into my, that is the multiplication of individual mean. And if any one of the process is having zero mean, then this rxy tau is equal to 0, because any one of mx or my can be 0, so it will be 0. So this will result, if you put rxy tau is equal to 0, so this will result into this relation, that is SZF is equal to SXF plus SYF. So it simply says that in case of if any process is having mean value 0, that result into the net additive power of the system is nothing but power of addition of power of individual system. So that is the outcome of this analysis in the case of power spectral density of some process. We will further use these properties in our subsequent analysis, then it will be much more clearer to understand. So this is all about the random process and the multiple random processes and their analysis, and in this particular lecture we specifically concentrated on the how this power spectral density behavior will represent the functional form. Clear? So as far as the references are concerned, I had prepared this presentation with the help of Fundamental of Communication System by John G. Prokes and Masood Salehi, and another book of where my interest is Principle of Communication System by Herbert Taub and Donald Schilling from McGraw-Hill Publication. Thank you.